Thank you very much for the introduction. I am Keita Suzuki from Keio University in Japan, and I am thrilled to be presenting our work titled Balancing Analysis Time and Bug Detection, Daily Development-Friendly Bug Detection in Linux. So, as all of you probably already know, static bug detection in Linux is fundamentally very important. There's been many efforts made both in the industry and in academia, and it's been proven itself to be very, very useful in finding bugs. In fact, tools like Clang Static Analyzer, CSA, coccinelle, or CPP check has been integrated already into the Linux makefile so that developers can actually use it in their daily development. And this explicitly means that it's being recommended to be used in daily development. Now, with these efforts being made, so these are usable from the Linux makefile, with these efforts being made, one question actually comes up to everyone's mind, right? Well, are these tools actually used enough in practice? Now, to investigate this, we actually conducted a very simple sampling of Linux kernel patches. And to our surprise, we actually found out that 40 out of 64 patches collected did not mention any use of tools in its patch message. Even though it's actually customary to credit the tools if the bug is actually found with a tool. This actually suggests that these bugs are actually found with other methods, such as manual inspection by the developers or bug reports after the bug actually manifests itself to the end users. And our further investigation actually reveals that out of 24 patches that's actually found with the tools, only 12 of the patches mention use of static analysis tools. Now, this actually suggests that static analysis tools are probably not used much in daily development as expected. So what exactly is blocking developers from using these tools in their daily workflows? Well, one major reason here may be the well-known trade-off which bug detection tools typically face. Tools typically suffer from the trade-off of analysis time and bug detection capability. And recent tools typically focus on utilizing on one end of the trade-off. So tools like Pata or Saber actually utilize bug detection capability, meaning that it tries to find a bug comprehensively in return of conducting a very thorough and long analysis time. For instance, Pata was able to find 454 new bugs in Linux, but it actually took 33 hours per analysis to actually find the bug. Now, on the other hand, tools like Clang Static Analyzer or CPP check actually focuses on making analysis time as short as possible. They achieve a short analysis time in return of very limited bug detection capabilities. For example, CPP check only requires around 2.5 hours to analyze the entire Linux, but only conducts intra-procedural analysis for most of the cases and very limited inter-procedural analysis, meaning that it can't actually find bugs that are interfunctional or inter-procedural. Now, in this work, we aim to explore a more daily development-friendly bug detection by exploring an approach that finds bugs while still maintaining analysis time as short as possible for the developers. Now, by leveraging such approach to a tool, developers can use tools rapidly to find bugs in their code while keeping the overhead incurred by the tool short and so that they can actually maximize their everyday development. To achieve our goal, we explore for the approach which does not consume time for analysis, but can be actually effective. To achieve this, we propose a combination of low-cost analysis techniques, namely the finger traceable analysis in this paper. This is actually a combination of 4 computationally low-cost analysis techniques. So in detail, first, finger traceable analysis characteristic is that we only conduct analysis for a single compilation unit. Second, we only look for field offset which is statically determinable. This means that we're only going to look at fields that have no whole field calculation, or fields like struct members or hard arrays with hard array numbers encoded. Third, we only conduct analysis with a very simple alias analysis. And lastly, we don't think of any indirect function calls with function pointers. We only look at the function with direct, which are directly connected. Now, I will be referring these finger traceable analysis as fit throughout this presentation. So focusing on fit analysis will be really effective in finding bugs in the first place. Now, to investigate this, we again survey the bug fixing patches in Linux kernel. We target 105 patches and investigate the required analysis to actually find these bugs. First, we actually checked if all 105 patches can be found with single compilation unit analysis. And we found out that 72 of the patches actually correspond to this. So 72 of the patches could be found with just analyzing a single compilation unit. Now, for these 72 patches, we conducted further analysis. We first checked if it required any offset calculation, and if it's actually a static offset analysis, or do we actually need dynamic offset calculation. Now, to our surprise, 65 out of 72 patches could be found with just static offset calculation. Now, then we actually checked if these patches required any alias analysis and how much it actually needed. To a surprise, 71 out of 72 patches only required intra-procedural alias analysis, and only one of them required complex inter-procedural analysis. Lastly, we checked if any indirect and function calls are involved in this patch, and found out that 65 of the patches did not have any indirect function calls. All of them are actually direct function calls. Now, in the end, we listed out all the patches which intersect with these characteristics, and found out that 64 patches can be found with this fit analysis. Now, this suggests that only leveraging fit analysis can actually indeed be impactful in finding bugs in Linux. Now, to demonstrate our claim, we designed and implemented Fix, a proof of concept framework which conducts our previously mentioned finger traceable analysis. Now, Fix is based on a well-known computationally low-cost data flow analysis, such as path-insensitive analysis, and field-based, meaning that we're not doing a fancy field analysis, but only looking at the field offsets and the member names of each field. And then we're doing a summary-based bottom-up inter-procedural analysis, which is known to be very efficient in achieving a short analysis time. And on top of these data flow analysis, we use our fit analysis as well. Now, to determine which bugs to actually collect, we use the well-known type state property analysis to define these bugs, which we'll actually talk to you in a little bit. And to achieve even more efficient bottom-up inter-procedural analysis, we introduced a technique named return code-aware inter-procedural state propagation. Now, as mentioned previously, we defined the bugs using the type state property analysis, which is a very well-known technique and which expresses each bug using a finite state machine, and determine the states of each variable and field each variable by looking at these state transitions. Now, in Fix, we determine the states of each variable and fields per compilation unit. Now, let's look at an example of type state over there. For instance, in the case of the double free bug, we define the states and transition at the state machine on your right-hand side. Now, let's say if we have a variable TBL, and the field val is the state that we're actually looking for. Now, val in the left code, let's say we have the initial state of init. On line 1, there's a free, so we transition the state from init to free. And then, again, we have free right over there on line 3. So we update the state again to the double free state and generate a warning state. It's just a buggy state. So it's pretty simple type state analysis transitions. Now that's our baseline collection of the states. Now the type state analysis is actually used in the interprocedural analysis as well for efficiency. Now to conduct an efficient analysis of interprocedural analysis, we conduct a bottom-up and summary-based analysis of interprocedural analysis, meaning that we analyze each call-Li first and propagate the final state of each argument to the caller. And we keep track of each analyzed states while we analyze it along. Now, for instance, in the, however, in some situations, a call-Li may have multiple final states for an argument. Now, for instance, on the code on the left-hand side, there are actually two final states in this code. One is when the call-Li actually returns minus error, and another is when they return a 0. If we actually look at the field val, when we return minus error, we free the val. But on the contrary, when we return 0, we don't do anything right over there. And on the other hand, the caller may expect a certain state from the call-Li. In the case of this one, basic block starting from line number 8, we're actually expecting a 0 return value, which is commonly a success state, and we're judging from the conditional clause in line 4. And if we pass a wrong state, such as the state of minus error, to this particular caller, which actually more expects a success state, we're going to have false positives because there's going to be a transition that shouldn't actually happen in the real world code. To avoid these issues, we introduce return code aware state propagation. Now, this state propagation keeps track of the final states of the argument per the return code in the call-Li and propagate expected states in the caller by checking how the return code is conditionally checked. Now, for fix, we focus on constant return codes such as error codes. Now, assuming that we have already collected these states in the call-Li, like as shown on your left-hand side, to determine which state to propagate to the caller, we first check the error code usages in the caller. In this case, it's going to be line number 4. Now, from the error code usage, we found out that the basic block starting from line number 5 expects a non-zero return value, which is commonly an error code. So we propagate the states coupled with this return code. In this case, it's going to be minus error. And we're going to propagate this free state to this line, basic block starting from line 5. Likewise, we propagate a 0 value state to the other basic block, often, and we propagate the state of a success state to the caller. By doing this, we will be able to propagate the expected states to the caller and will lead to less false positives. Now, we implemented fix using the LLVM compiler framework and defined states for 6 bug patterns. And we generated compiler extension warnings, which can be embedded into the Clang compiler, which is already available in Linux makefile. Now, developers can use the fix embedded Clang as they normally would in the makefile. And when running the build of the Linux kernel, fix will generate warning just like a compiler warning, while still generating build artifacts as well. To evaluate fix, we specifically look into 3 questions. 1, what is fix's bug detection capabilities? 2, how long does fix take to analyze Linux? And 3, how does fix actually perform compared to other tools? We're going to be answering these questions throughout the rest of this presentation. Our analysis is run on Linux kernel version 5.15 using the OS config. Now, firstly, we check the bug detection capabilities by looking at the bug reports generated by fix. Now, in the end, fix was actually able to find 47 new bugs in Linux, which 13 of them were actually confirmed and fixed by the developers. Now, when looking at each bug type, We found out that double free had there were many double frees in the code with 21 bugs found by Fix, followed by use after free, double lock, double unlock, memory leak, and reference counting errors, adding up to 47 true positives. Now, this is one of the case studies we found bug in the Linux kernel, which is a double free in AMD GPU driver. In line number 3, we call initialization function to initialize and allocate an initialized array elements in a struct. In the callee, if it actually encounters an error, it frees the array itself and returns enum. The caller captures this error and calls a destructor. And destructor, again, destructs many components and frees the array again, leading to a double free. As I said, this bug was actually confirmed and fixed by the developers themselves. And it actually existed from 2016, so it's around a 7-year-old bug in the code. Next, we checked the analysis time of Fix. In total, Fix actually required around 2 hours and 33 minutes linear time to analyze the entire Linux kernel. And when looking at individual source file analysis time, Fix only required less than 1 second for 90% of the source files. And even if you look at the 99th percentile, Fix only required 3.79 seconds for 99% of the source file. OK, finally, we check how Fix perform in the wild and compare how it performs versus the existing tools. We're going to be comparing Fix with the two existing tools, CSA and CPP check, which are both tools that can be directly used from the Linux make files already integrated into Linux build. And we focus on the following questions. Well, how did Fix do comparing the analysis time? How did Fix actually find bugs? How about the other competitors? And lastly, we're going to be looking at the false positive rate over there. Now, first 2 questions, we're going to be checking this by analyzing the 13 developer confirmed bugs. And then for the false positive rate, we're going to be looking at the entire Linux kernel. Now, for analysis time, Fix was actually able to outperform Clang Static Analyzer and achieve similar performance with CPP check. In long cases, as the middle one in trace events hist, Fix was actually able to achieve 25 times short analysis time versus CSA, only requiring around 1.69 seconds. And even comparing with the CPP check, we performed like around 4.3 times faster versus CPP check. Now, let's look at the bug detection capabilities. When looking at the bug detection capabilities, unfortunately, CSA and CPP check could not find the 13 bugs that were actually found by Fix. Now, this difference mostly comes from the previously mentioned difference in the interprocedural analysis phase. As mentioned before, CPP check has very limited, only conducts very limited interprocedural analysis to achieve short analysis time. And Clang Static Analyzer, while it does a very comprehensive analysis of a compilation unit, it limits to 2 call depths because of its use of very sophisticated top-down interprocedural approach. Fix, on the other hand, uses the return code velocity propagation in interprocedural analysis to efficiently conduct interprocedural analysis, both in bug detection capabilities and short analysis time. Now, finally, we will briefly talk about the false positives. As you guys probably already know, false positive is a crucial part of static analysis bug detection tools. When actually comparing the false positive rate of analyzing the entire Linux, Fix was actually able to generate less false positive compared to Clang Static Analyzer and CPP check reported false positives rate of CSA and CPP check. With Fix, actually, the rate around 61%, while the other 2 were around 83%. So in terms of false positives, we were able to achieve less false positives compared to these competitors. Okay, to summarize, Fix's goal is to provide a daily development-friendly bug detection by using a combination of 4 low computational analysis. We were able to find 47 new bugs in Linux kernel version 5.15, 13 of them being confirmed by developers. And looking at the analysis time, only less than 1 second of analysis time for 90% of the source file. And we were able to outperform CSA and CPP check performing in the wild. Okay, thank you very much.